Okay, here are 6 KSP sample problems. By the time you've gone through each of them, if you feel comfortable with them, you should have a good understanding of KSP. Since there's 6 problems here, I'm not going to do each one in great detail, but I will show the detailed mathematical solutions. Pause at any time if you want to understand more detail. Calculate the solubility of barium sulfate given its KSP. Well, that means that 1.1 times 10 to the minus 10th equals the concentration of the barium ion times the sulfate ion. Therefore, we can call that S times S, and S is the solubility of barium sulfate. So all we got to do is take the square root of the KSP to get the solubility in moles per liter, which is 10 to the minus 5th moles per liter. Don't forget that one of these forms one of those and one of those. So the concentration of the ion, in this case, barium ion, is the same as the concentration of the sulfate ion, and it's the same as the concentration of the barium sulfate, which did dissolve. Okay, so that would be the solubility in moles per liter. If we multiply by the molecular weight, we get grams per liter. Here's a similar problem, but this time it's CAF2, so it's not a 1-to-1 ratio. They want you to calculate the KSP. Well, we can write out the equilibrium expression, which is equal to the calcium ions times the fluoride ions squared. See how we get that from the dissolution here? And therefore, it's an S times 2S quantity squared situation. Or you could go directly and realize it's a 4S cubed type of situation. In other words, this is the concentration of the calcium ion. We must have twice as many fluoride ions. We multiply these through. Don't forget to square this. And you get 5.5 times 10 to the minus 11th is the KSP value. Now they want solubility given a KSP again. So here's another situation where we're doing it. So 5.2 times 10 to the minus 11th must equal the S times 2S quantity squared, right? See that? It's also the same as 4S cubed. We could then solve for S, which is the solubility of magnesium fluoride in moles per liter. And it's 2.4 times 10 to the minus 4th molar. They want grams per liter. Multiply by the molecular weight, and you get grams per liter. They give you the solubility of calcium sulfate, and they want you to calculate its KSP. Well, KSP for calcium sulfate, even though it's plus 2 and minus 2, must just be an S squared situation. Right? And so therefore, 0.67 grams per liter is the number we will be squaring, but that's grams per liter. To go to moles per liter, simply convert from grams per liter to moles per liter using the molecular weight. So it's 0.049 molar for each ion. Square it to get the KSP, 2.4 times 10 to the minus 5th. Given the solubility of copper hydroxide, calculate it given KSP. So KSP to solubility once again. So geez, all these problems are very similar. So KSP must in this case be a 4S cubed situation. So we're going to take, given that number, 2.2 times 10 to the minus 20th, to calculate the solubility S. Solving for S, we have to take 1/4 of the cube root of that, given 1.8 times 10 to the minus 5th. Fine. To convert to grams per liter, multiply by its molecular weight. And why do we need KSP in general? And why not just have some solubility tables that give percents? KSP divides it up into each ion. That way it can show the common ion effect and gives you a more detailed understanding of what's going on. It also creates a commonality between all these equilibrium situations, be they buffers, be they weak acids, be they ions. It's all using the same system.